There's a wall where space and time fall apart. It is the Planck wall where physics stops predicting. Put bluntly, it marks the limit of classical physics. Net result, it separates calculable physics from the unknown. A tiny surface of reality defines the Planck scale in length. It measures about 10 to the negative 35 meters. This scale decides whether space looks smooth or wildly quantum. Gravity treats space as continuous geometry, like a stretched sheet. Quantum mechanics makes positions uncertain, jittering at tiny scales. A proton spans about 10 to the negative 15 meters for comparison. Compare that to the Planck length, which is 20 orders smaller. So the Planck scale marks where our smooth space idea fails. Physics fails at that wall because two rules violently clash. Those rules are gravity and quantum mechanics. Each dominates different domains. General relativity needs smooth geometry to describe gravity's pull. Quantum theory allows probabilities and fuzziness at the smallest scales. Near the Planck scale, both descriptions give contradictory predictions. Calculations blow up into infinities, which break physical sense. Extrapolating general relativity to microscopic distances predicts infinite curvature. Those infinities mean the math stops mapping to reality. Thus, the core problem is a mismatch between smoothness and quantum jitter. At the Planck wall, space becomes foamy and fundamentally uncertain. That change would rewrite how positions and time behave. Quantum fluctuations reach the same scale as space itself, causing geometry to fuzz. Instead of smooth distances, you get probabilistic distances that vary each measurement. Quick mental image, a calm ocean turning into microscopic boiling bubbles. Concretely, wavelengths shorter than about 10 to the negative 35 meters lose meaning. So the Planck wall swaps smooth geometry for a chaotic quantum landscape. Physicists build candidate theories to step across that wall. If one theory wins, it changes every small-scale prediction. String theory replaces particles with tiny vibrating strings that spread energy. Loop quantum gravity builds space from discrete chunks, quantizing area and volume. Each approach removes certain infinities by changing geometry's fundamental rules. For example, string theory spreads a collision's energy along a string. That spreading tames singular behavior, making equations finite and sensible. So quantum gravity proposals rewrite space to restore predictive physics. Testing the Planck wall needs extreme natural laboratories like black holes. Those settings concentrate energy high enough to reveal Planckian effects. We search for indirect signals left behind by quantum gravity. Gravitational waves and the cosmic microwave background carry subtle fingerprints. Precise measurements can reveal tiny deviations from standard predictions. A primordial signal might change polarization in the cosmic microwave background. Detecting that change would point to Planck-scale physics in the early universe. Therefore, we hunt indirect imprints where direct experiments cannot reach. Energy at the Planck scale is enormous in practical units. Reaching those energies in a lab is effectively impossible. Planck energy corresponds to about 10 to the 9 joules concentrated at a point. That energy density dwarfs particle accelerators like the Large Hadron Collider. The LHC reaches only tiny fractions of the Planck energy by many orders. Hence, we rely on astronomical events, not collisions in human machines. So the sheer energy gap forces indirect observation strategies. If the Planck wall governs reality, cosmology would change profoundly. Early universe dynamics and black hole interiors may behave very differently. Quantum gravity could control the universe's birth, replacing classical equations. Singularities might become quantum regions, or even bounce back into expansion. Those changes could leave traces in late-time observables like radiation spectra. One concrete prediction is slight deviations from Hawking's black hole radiation. Measuring such deviations would hint at Planck-scale corrections in black hole evaporation. So the Planck wall can reshape cosmic origin stories and black hole fate. We started with a bold claim, a wall halts prediction. That is still the picture. The Planck wall marks physics' limit. If you want more, subscribe for calm visual breakdowns of mysteries. Bottom line, the Planck wall marks where our equations end.